Hello everyone. This video is on the Knewton Alta assignment for section 5.6, part 2, called Graphs of Rational Functions. Alright, so in this video, I'm going to be going over a preview version of this assignment. Please understand that the questions I see in this video may not be the same questions that you see when you do the assignment yourself. But all the objectives are the same, so I'm hoping that watching me do a few of these here helps you out in some way when you go to work on the assignments on your own. Alright, so on your assignment page you have the title, mastery bar, you can see the objectives. Looks like there are 3 objectives for this assignment. Under the current objective, there should be a question related to that objective, and then at the bottom of every question there should be a feedback button where you can send feedback to Knewton if you have any issues. You will not have this instructor cheat button. Alright, this is instructors only. But you will have a more instruction button. Alright, and if you're ever struggling with a topic, try clicking on this and you'll be taken to some reading or some videos on that topic, and you'll be given some questions related to that instruction, and you can get through the assignment working through those if you wish. Alright, so this first objective is find the equation of a rational function from a graph. Alright, so before I get into this actual question here, I want to talk about, how we're going to do this. Alright, so remember, a rational function, you should know what these are from section 5.6 part 1, but I'll refresh your memory a little bit here. Right, a rational function can take the following form. Any function that can take the following form. F of x equals, p of x divided by q of x. It's a fraction. Any function that can be written as a ratio, a fraction of 2 polynomials, right, where p and q are polynomials. And you should know what polynomials are based on earlier sections of chapter 5. And of course, we want the denominator to not be 0. Right? You can't divide by 0, that's undefined. Alright. Now, apart from this, we can express every rational function in the following way. And this is the kind of equation I'm going to write in this objective. We can express every rational function as the following. F of x equals, say, some number a. Alright, this is called a scale factor, times, and then your fraction. So really a is kind of coming from the lead coefficient of the numerator and the lead coefficient of the denominator polynomial, this factor a out here. And then if you remember how polynomials go, if you know all the zeros, you can write it in factored form as x minus, say the numerator is, I'm calling p. I'll call each of the zeros, p1, p2 up to p whatever, right? So x minus p1 times, say, x minus p2, and so on up until x minus pn if it's a degree n polynomial, and then the denominator, same thing. I'm calling this q, so I'll call all the zeros of the denominator polynomial q's, q1, and x minus q2, and so on up to, x minus qm if it's a degree m polynomial. Whatever the degree, however many, whatever the degree is, that's how many factors you can write. So again, p1, p2, and so on. These are the zeros of the numerator polynomial, p of x. And q1, q2, and so on. Right, these are the zeros of the denominator polynomial, q of x. Okay. Now, when I say we can write it this way, of course, I want it to be in simplified form. So I'm just going to say, assume this is simplified, meaning that the numerator and denominator don't have any common factors. Right? Right. So if the numerator and denominator don't have any common factors, it's in simplified fashion like this, then we can look at the zeros of the polynomials and see what's going to happen on the graph. Right. So all the zeros of the numerator in simplified form, I'll just say let's assume it's simplified. Right, the zeros of the numerator will show you where the x-intercepts of the graph are. All right, so where is the graph hitting the x-axis? And we also need to look at the multiplicities of these zeros. Now that should also be a familiar word to you from earlier in chapter 5. So if you're looking at the zeros of the numerator, talking about the x-intercepts, if it's a zero with an even multiplicity, then the graph will bounce off. Remember, the graph bounces off the x-axis at that x-intercept. So say here's the xy plane, here's the x-intercept. Remember, the graph's going to do something like this. It might be above it, it might be below it, but it'll come down, touch the x-axis, and then bounce off. Right? Stay on the same side of the x-axis. But if it's a zero of the numerator with an odd multiplicity, remember, then the graph crosses over the x-axis at those x-intercepts. So I'm hoping this all sounds familiar. Right? You've seen this before. So the graph is going to come up, hit the x-intercept, and then cross over to the other side, right? Whether it be from above or below, like this, whatever. All right. So the zeros of the numerator will dictate where you're going to find the x-intercepts, and their multiplicities will dictate, how the graph behaves at those x-intercepts. Will it bounce off the x-axis? Will it cross over? Now the zeros of the denominator in simplified form, you've also seen in section 5.6 part 1. When you simplify a fraction and, whatever makes the denominator 0 in that simplified fraction is where the vertical asymptotes are going to be. Right, so the zeros of the denominator, that q of x, these are going to show you where the vertical asymptotes are located. Alright, now here's something that wasn't discussed in section 5.6, part 1. What about the multiplicities of these zeros? Well, if it's a zero with an even multiplicity, then what's going to happen around that vertical asymptote is the graph will approach the same direction on both sides. Graph approaches same direction on both sides of the asymptote. And here's what I mean by that in a picture. Same direction on both sides. So that means, say here's where the vertical asymptote's at. And I'll put a little dashed line here. What I mean by that is the graph will either go to infinity on both sides, right, go up forever on both ends, on both sides of the asymptote, or go down forever on both sides, right? Again, say here's the vertical asymptote, this dotted line. The graph will go down forever on both sides. That's what I mean by the graph approaches the same direction on both sides. So if there's a zero of the denominator with an even multiplicity, one of these things is going to happen around that asymptote. And then if it has an odd multiplicity, well, then the graph is going to approach opposite directions on both sides. Graph approaches or goes in opposite directions on each side of the asymptote, or on both sides. I'll say approaches opposite directions. All right. So what I mean by that, again, here's say the vertical asymptote, little dashed line here. What I mean is that on one side the graph's going to go to infinity, and then on the other side the graph will go to negative infinity. All right, or the other way around, right? Or, again, here's a vertical asymptote. Maybe on the left side it'll go to negative infinity, on the right side it goes to positive infinity, but they'll go in opposite directions if that zero of the denominator has an odd multiplicity. All right, so again, this wasn't discussed in section 5.6.1 part 1, but it is now. All right. Okay. So that should be enough information to be able to write an equation for a rational function based on its graph. So if we look back here, right, this graph, they're telling us, it has an x-intercept at -1, and you see that here, right? The graph touches the x-axis at -1, and you see it crosses over. So the graph's going to have an odd multiplicity, and they want the smallest degree possible, so I'm going to say it has a multiplicity of 1 because it kind of crosses straight through. And it also has a y-intercept at -2, +2, so 0, 2 here. Now that point, the y-intercept, we're going to use that to find that a, that scale factor. And it has a vertical asymptote at 1. All right, so again, I'm going to draw a little rough sketch of this actually. All right, so 0, 2 was the y-intercept, -1, 0 was the x-intercept, and it has, a vertical asymptote, x equals 1, and the graph looked, something like this. And then approaching, the x-axis to the far left, and doing something like this over here, approaching the x-axis again. So it has, it has the x-axis as a horizontal asymptote, right? Y equals 0 is a horizontal asymptote. And remember what that meant from section 5.6 part 1? That meant the numerator had a smaller degree than the denominator. Right? Numerator has smaller degree than the denominator. I'll just write numerator has smaller degree. That's so if the x-axis is a horizontal asymptote, the numerator is going to have a smaller degree. And again, x equals 1 is a vertical asymptote. That means x equals 1 is a 0 of the denominator. polynomial. And because the graph is going in the same direction on both sides, it's going to have an even multiplicity with even multiplicity. And again, they're trying to keep this as small as possible. So I'll just say with a multiplicity of 2. Right, that's the smallest even number. All right, so I'll just say 2, a multiplicity of 2. And -1 is an x-intercept. Right? So x equals -1. Right? An x-intercept, that's going to be a 0 of the numerator. Is a 0 of the numerator. And since it's crossing over the x-axis, right, not bouncing off, this is going to have be a 0 with an odd multiplicity. And once again, just to keep things as small as possible, I'll just say it has a multiplicity of 1, right, the smallest odd number. All right, so here we go. Remember that little form I said earlier where we have f of x equals a times and then some fraction, and we'll find this a later with some other point on the graph, and that'll be the point 0,2 here. And this is the point 0,2 is on the graph. This is, I'm going to use some other point to help me find this a, this scale factor later. All right, so again, the numerator has only the 1, 0, -1, so it has a factor of x plus 1 to the first power. Right, the multiplicity is 1, so x plus 1 to the first power. And x equals 1, right, for vertical asymptote, that's a 0 of the denominator. So x minus 1 is a factor. Remember the factor theorem, right? X minus 1 is a factor of the denominator polynomial, but because the graph, again, is going in the same direction on both sides, it's got to have an even multiplicity, a multiplicity of 2, I'm going to say. Put a power of 2 on that, right? X minus 1 squared. All right, so now I just need to find a. So we know the point 0,2 is on it, right? 0,2 is on the graph. And so I replace x with 0, replace f of x with 2, and we get this equation. 2 on the left equals a times, 0 plus 1 to the first, and 0 minus 1 squared, well, that's just 1 over 1, so a equals 2. A equals 2. I just pop that in, and we get the following function. F of x equals 2 times, and then this fraction with the quantity x plus 1 in the numerator, and the quantity x minus 1 squared in the denominator. And this is, I think, all they want, the factored form of this. Now, if you want, you can put the 2 in the numerator and say 2 times x plus 1, that's 2x plus 2 in the numerator. And if you actually multiply the denominator out, take x minus 1 and square it, that'd be x squared minus 2x plus 1. This is the same exact thing. So I think either one is going to be acceptable. But I think you can just put it in the factored form. All right, so I have the scale factor 2 times, and then the quantity x plus 1 divided by, and then the quantity x minus 1 squared. And I believe this should be good. Right. Great. All right, and yeah, that's exactly how they have it. Right. And again, after you submit an answer, it'll tell you if you're right or wrong, and give you some sort of answer explanation. Please read through, the answer explanations, just to make sure you understand why something was right or wrong, and you can hopefully learn from your mistakes for the future. Right. Okay, the next question, find the intercepts of a rational function. Well, you should know how to find intercepts by now. X-intercepts, Y-intercepts. So yeah, so that's all they want down here. Now notice they have the parentheses and the commas already. You're just putting the x and y coordinates for this particular problem. Alright, so I'll write this function out. This should be, in my opinion, the simplest of the objectives, because you should know how to find intercepts of graphs at this point from earlier chapters. Right, so we're given f of x equals. Now the nice thing is, for this particular problem anyway, they give us the function, where the numerator polynomial and the denominator polynomial are already factored, right? The numerator has x plus 1 times x minus 9. The denominator factors are x plus 3 times x minus 2 times x minus 1. Right. Now I believe the easiest is the y-intercept. Remember, for y-intercept, that's 0, comma, whatever. You just plug in x equals 0. You plug in 0 for x. And then the y value is what's f of 0, right? So what is f of 0, right? Plug in 0 for x. Well, 0 plus 1 is 1 times 0 minus 9 is negative 9. And then the factors in the denominator are 3, negative 2, and negative 1. Right? 3 times negative 2 times negative 1. And so we have negative 9 in the numerator, positive 6 in the denominator, and when you reduce this, this would be negative 3 halves, or negative 1.5, if you want to write a decimal. But there's your y-intercept. And then for the x-intercepts, just, remember all those look like this, something comma 0. You just need to find the x-coordinate. So you let f of x equals 0, right? Let the output be 0. So we have 0 equals this x plus 1 times x minus 9 divided by, and then x plus 3 times x minus 2 times x minus 1. Really, the denominator, as long as the fraction is simplified already, which it is, right? This is a simplified fraction. I mentioned this earlier, right? If your fraction's simplified, the zeros of the numerator are where the x-intercepts are. So you don't even need the denominator, right? Just what makes it, if it's simplified already, which it is, right? There's no common factors in the numerator and denominator. Just what makes the numerator 0? Because you can multiply both sides by the denominator and, it gets rid of it, because 0 times anything is 0. And then you would just have this, and the solutions of this equation, when is x plus 1 times x minus 9 equals 0, or when x equals negative 1 and x equals positive 9, right? So negative 1, 0, 9, 9, 0, those are the x-intercepts. Those are what they want me to enter. And if you want, you can go to some graphing calculator, desmos.com, or whatever graphing calculator. When I punch this in, and you'll see that these are the points where the graph crosses the y-axis and x-axis. All right, so the y-intercept, 0, comma, negative 3 halves, right? Negative 1.5. Then the x-intercepts were at negative 1, 0, and 9, 0. That should be good. Okay, great. All right, next question. All right, so now we're into graph rational functions. So again, here they're having us move. It's one of those like interactive graph ones where you move some stuff around. So it says graph the function given below by moving the vertical asymptote, then the value of the x-intercept. Finally, select the correct end behavior. All right. The x-intercept 2, 0 is already provided for you. So remember, the zeros of the numerator are where the x, if it's simplified, which this is, the zeros of the numerator are where the x-intercepts are going to be. So 2, 0 and 5, 0. So move the other x-intercept to 5, 0. All right, there we go. That's it, 5, 0. And then remember, the zeros of the denominator make tell you where the vertical asymptotes are, which would be at x equals 3. So I need to move this point here to 3. Right. There's 3. Right. X equals 3, because that's 2, that's 5. Here's x equals 3. So there we go. All right, and then finally, what kind of end behavior do we want? All right. This or this. Now, look at this. When I have the dot in the second box here. See, the graph is approaching y equals positive 1 on both ends. When I have it here, the graph is approaching y equals negative 1 on both ends. Well, look at this. If you were to multiply this out, the lead term in the numerator would be x squared. The lead term in the denominator would be x squared, right? They have the same degree. So they're going to have this is going to have a horizontal asymptote, and this was discussed in 5.6 part 1, so I'm not going to write this out. When they have the same degree, to find the horizontal asymptote, you just divide those lead terms, right, to find the quotient. X squared divided by x squared is 1. Y equals 1. Positive 1 would be the graph that the thing is approaching on the ends. So not this one, right? This is approaching negative 1 on both ends. So I would like to change this to the other one where it's approaching positive 1 on both ends. And here you go. This is the graph that you would see in Desmos as well. If you were to enter this in Desmos, desmos.com, you'd see this exact same graph. And that's all they asked us to do. Right. Great. And again, please read through your answer explanations. Alright, so graphing again. Right, and see another the same exact kind of problem. Got to move these black dots here on the dotted lines to move the asymptotes, the vertical asymptotes. This other dot is where x-intercepts are, and then we change the end behavior, depending on how it's supposed to go. Alright, so the numerator has x plus, now again, it's simplified. The numerator has x plus 2, so the x-intercept's at negative 2, 0. Move this over. No, should be at negative 2. The denominator has x plus 4, x plus 1, so negative 4 and negative 1 are where the asymptotes are. So negative 4 and negative 1, like that. And you got the x-intercept at negative 2, 0. And notice the degree of the denominator is bigger. It would be an x squared, it would be a degree 2. The numerator is degree 1. So the graph is going to approach y equals 0, which it does here. Let me see if I change the end behavior. Alright, so it still does that. So both end behaviors are correct. It's just the way the graph's moving. Alright, so we have to determine local behavior, actually. Alright. Well, let's see. What would be the y-intercept? Right, because both of these have different y-intercepts. See how the graph crosses the y-axis at different points? So let's find the y-intercept. If I were to plug in 0 for x, the numerator would be 2 and the denominator would be 4. So the y-intercept would be positive 1/2, which this one looks like. Right? If I change the end behavior here, it looks like the y-intercept's at negative. But I want a positive y-intercept. So the only graph that really matches all the information I know about this function, where the vertical asymptotes are, where the x-intercepts are, and where the y-intercept is, in the end behavior, the graph's approaching y equals 0 on both ends, this is the only one that matches. So you got asymptotes and intercepts. Right? That's why those other two objectives are here in this, asymptotes and intercepts, writing equations. Is that's all you should need to be able to move these graphs around. Alright, so back to finding intercepts. Again, I should be able to do this pretty quickly. The function simplified. The numerator has factors of x minus 12 and x minus 4. So 12's, now it's just asking for the x-intercepts. So 12, 0 and 4, 0. That's where the graph would cross the x-axis, and that's it. Right? They do not want the y-intercept, notice. Right? Very simple. Alright, then now they want the y-intercept. Oh my goodness. Right? So if I plug in 0 for x, the numerator would be negative 12 times negative 4. The numerator would be 48, and the denominator would be 6. Negative 3 times negative 1 times positive 2. 48 divided by 6 is 8. So 0, 8. 0 for the input, 8 for the output. Right? It's that simple. You just plug in 0 for x, your output's the y-intercept. Wonderful. All right. So now find the equation of a rational function from a graph. All right, so again, I'll do this. Let's see if we can see my paper and put the graph up here a little bit. You can see a little bit of it. All right, so this one, and I want to point out the x-intercepts. Hopefully I'm writing big enough for you. And once I write out all the pertinent information, I'll make the paper bigger. Just at -1. Just x equals -1. And notice that the graph does cross over. All right, crosses over the x-axis, so it'll have an odd multiplicity. I'll just put odd mult. And to make it as small as possible, I'll just say it has a multiplicity of 1. And that's the only x-intercept. The y-intercept, did they tell us the y-intercept? Nope, but they are telling us the point 1, -2 is on the graph. So the point 1, -2 is on the graph. That's going to help us find that scale factor of a. And the vertical asymptotes are at x equals 0, right? The y-axis. You can hopefully see this here, right? My cursor moving up and down. It's really tiny, I'm sorry. But the y-axis, x equals 0. And notice the graph is going in opposite directions on both sides. To the right of x equals 0, it's going down forever. To the left of x equals 0, it's going up forever. So this is going to have an odd multiplicity, odd mult, right? Or I'll just make it a multiplicity of 1. But there's another vertical asymptote, and that looks like at x equals 2. With also an odd multiplicity, again, because the graph is going down on the left of 2 and up on the right of 2, right? It's going in opposite directions. So again, with an odd multiplicity, odd mult. And that's all the information I should need, right? Oh, and I guess, the horizontal asymptote is y equals 0. Just keep that in mind. That just means the degree of the numerator should be smaller than the degree of the denominator, right? The horizontal asymptote looks like it's y equals 0. And that's enough information to be able to write the equation. So we have f of x equals, some scale factor a times a fraction. Numerator, comes from the x-intercepts. Now x equals -1 is a 0 with a multiplicity of 1, let's say, odd. So the quantity x plus 1 is a factor up there to the first power. And then, the denominator comes from where the vertical asymptotes are, the denominator factors. X equals 0, so x to the first with an odd multiplicity, right, to the first power. And then x minus 2, also to the first power. And the numerator would be a degree 1, the denominator would be a degree 2, so the numerator has a degree less than the denominator, so the horizontal asymptote would be y equals 0, so this fits. And now I just use that the point, 1, -2 is on the graph, so -2 is the output, and 1 is the input. So a times, and then 1 plus 1 in the numerator, 1 times 1 minus 2 in the denominator. This would be 1 over -1, so negative a. So the value of a is positive 2. The value of a has to be positive 2 here. And put that in and we get our function. F of x equals, 2 times, and then numerator has the quantity x plus 1. You can also put that factor of 2 in the numerator, it's the same thing. And the denominator has factors of x and x minus 2. This is totally cool. Or, if you want to multiply it out, the numerator would be 2x plus 2. The denominator would be x squared minus 2x. And this should also be acceptable. They're the same function, right? And they'd have the same x-intercepts, the same vertical asymptotes. The point 1, -2 would be on the graph. So going back to the assignment, that's what I'll enter. I'll enter it in the factored form again. All right, so we have 2 times the quantity x plus 1 in the numerator, and then x times the quantity x minus 2 in the denominator, and that should be good. Oop, what happened? What happened? One negative 2 is on the graph. Alright, so it's giving me an option to try again. Maybe it wants, I don't know why they would want the factored form in one version and not factored in the other. You know what, let me go to Desmos and see what this graph looks like. The graph of the function I just wrote. 2 times the quantity x plus 1 divided by, and then x times x minus 2. And see, it's got the point 1 negative 2 on it. Or no, it doesn't. Why? Oh, no, I did make a mistake in the calculation of A. So glad that came up. You might have been screaming at me. I'm sorry. Yeah, 1 plus 1 is 2. 2 divided by negative 1 would be negative 2a, so a is positive 1, not positive 2. My apologies. So yeah, glad that error. I'm glad they're giving you another shot here. You know, and you probably have noticed that a lot of times if you do get something wrong, it'll give you one more chance to fill it in. So the value of a is just 1. So it should just be x plus 1 in the numerator and x times x minus 2 in the denominator. That, yes, that was correct. So I made a misstep in the calculation of a, and I do apologize for that. You know, I didn't see that 1 plus 1 was 2. So just don't rush things, huh? Good lesson there. Check your work. Should have checked it on Desmos, but anyway. Next question. So now we're back to finding the intercepts. Again, this should be quick. This is simplified, no common factors, right? So the numerator zeros are the x-intercepts, negative 2 and 4. So negative 2, 0 is one of the x-intercepts. And positive 4, 0 is another x-intercept. And they also want the y-intercept. Looks like they want all x or y-intercepts. So for the y-intercept, I plug in 0 for x. If I plug in 0 for x to all these, you'll have negative 8 in the numerator, 2 times negative 4. And then 4 times negative 5 is negative 20, times 1 would be negative 20. So negative 8 over negative 20, that would reduce to 2/5. So input 0, output 2/5, or 0.4 if you want a decimal, but I'll put the fraction. There you go. The intercept objective should be the easiest one in my opinion. Alright, so now we're back to graphing. So again, this is just one where you're moving a bunch of points around. Again, we have a function here where everything's factored and it's simplified. So the vertical asymptote would be at x equals 1. There we go. Move the asymptote to x equals 1. The x-intercept would be at 3. So I move it from negative 1 over here to 3. That's 4. 3. And for the end behavior, and just I think just make sure the y-intercept is correct. If you were to plug in 0, the numerator would be negative 3, the denominator would be 1, right, because it's being squared. Negative 1 squared is 1. So 0, negative 3, this looks like good, and the numerator has a smaller degree than the denominator, so it should be approaching the x-axis on both ends, which it is here, and the y-intercept looks good, x-intercept looks good, vertical asymptote, horizontal asymptote, everything looks good with that one. See, if I move it, it changes the y-intercept to 0, positive 3, but it should be at 0, negative 3. Alright, so this graph is the better one. Great. Alright, moving on. Alright, so one more of these with the moving stuff around on the graph. Alright, so this should have a vertical asymptote at -5, right? That makes the denominator 0, so I move the asymptote over to x equals -5. The x-intercept should be at -6, right? The numerator is x plus 6. Move the x-intercept over to -6. And the y-intercept would be positive 6/5, which, 1 and 1/5, that's looking like it about here. And the horizontal asymptote should be y equals 1, right? X over x, which it looks like the graph is approaching here. Now if I flip the end, see, this is y, the ends are approaching -1. The y-intercept is negative. This is not the graph that I want, right? I want the y-intercept to be positive and the graph to be approaching y equals 1 on both ends, so that end behavior is correct. Wonderful. All right, so that objective's done. And then back to the last couple problems should be on writing those equations. Finding the equation. All right, so here, x-intercept's at -3. It's got an odd multiplicity. The graph's crossing over. Y-intercept is at 0, 3/2, they're telling us, right? And there's a vertical asymptote at -2. But notice the graph is going on, in the same direction on both sides of x equals -2, so it's going to have an even multiplicity. All right, so I'll write all that stuff up. So again, x-intercept is at -3, 0 with a odd multiplicity, right? The graph crosses over. X equals -3. Y-intercept is the point 0, 3/2, right? They told us this. And this is going to be used to find the value of that a if I actually do it correctly this time. And then the vertical asymptote, I'll just put VA for vertical asymptote, is at x equals -2. But again, the graph is going in both direction, the same direction on both sides. So it's going to have, I'll have an even multiplicity on this. All right, so we have f of x equals, some scale factor a, which I don't know, times the numerator comes from the x-intercept, so it'll be the quantity x plus 3, and since -3 is a 0, and I'll make it to the first power, odd multiplicity. And where the vertical asymptotes are tells you how to find the factors of the denominator polynomial. X equals -2, so x plus 2, right, minus -2, but to an even power, right? And I'll keep it as small as possible to the second power. And it did have a horizontal asymptote of y equals 0 again. Right, see, the horizontal asymptote is the x-axis, so the numerator should have a smaller degree, which this one does. This would be a degree 1 divided by a degree 2. So everything's looking good so far. Now I just need to use the point that I know, which is the y-intercept here, to find the value of a, right? So 3/2 for the output, 3/2 over here, equals, and then when x is 0, this would be 3 over 4, right? 2 squared. So 3/4 a. So a must be 2. Right? Multiply both sides by 4/3. You get 4 over 2, which is 2. All right, so we have f of x equals 2 times the quantity x plus 3 divided by the quantity x plus 2 squared. And if you want to multiply that out, you can, but I'll leave it in factored form. All right, so we have 2 times the quantity x plus 3 in the numerator divided by the quantity x plus 2 squared in the denominator. And this should be good. I'm looking at it again, trying to double check my work this time. Didn't make any arithmetic errors like earlier. This should be good. All right, and we should have just one more of these. Yeah, so again, we have just one x-intercept at x equals 3. The graph's crossing over, so it's got an odd multiplicity. They're telling us the y-intercept is at 0, -3/4. We'll use that to find the a, that scale factor. And once again, the vertical asymptote's at x equals 4, and it's going to have an even multiplicity again because, again, on both sides of this, the graph's going in the same direction. All right, so I'll just flip this over. So again, I'll write all that information out. The x-intercept is at 3, 0, x equals 3, and it's going to have an odd multiplicity. The graph's crossing over, and I'll just give it a multiplicity of 1. The y-intercept is the point 0, negative 3/4, and I'll use that to find that A vertical asymptote. Let's put VA is at x equals 4, and that's going to give me a factor in the denominator, and it's going to have an even multiplicity again because the graph was going in the same direction on both sides. And I'll just make it a power of 2 to keep it as small as possible. And the horizontal asymptote was y equals 0 again, right? It was the x-axis. The graph was approaching the x-axis on both ends. So again, all this tells me is that the numerator should have a smaller degree than the denominator. All right, so we have f of x equals a times, some fraction. The numerator would have a factor of x minus 3, and I'll just keep it to the first power. Odd multiplicity. The denominator would have a factor of x minus 4, but twice, right? Even multiplicity. And this has the setup where the degree of the numerator is smaller than the degree of the denominator. So this would have a horizontal asymptote of the x-axis, y equals 0. So we're good so far. Now I use the y-intercept, right, to find this a. So we have negative 3/4 for the output equals, now if x were 0, this would be negative 3 divided by 16 times a, and then I multiply both sides by negative 16/3. The negative 3's would cancel. 16 divided by 4 is 4. The value of a has to be 4. All right, and I'm putting that back in here. So we have our function is 4 times the quantity x minus 3 divided by the quantity x minus 4 squared. And that's what I'll enter. So 4 times the quantity x minus 3 to the first, or 4x minus 12 if you multiply it out, and then the denominator is x minus 4 to the second. Again, you can multiply that out and make it x squared minus 8x plus 16, but I don't think we need to do that. Great. All right, and that should be it for this preview version of this assignment. As I said at the top of the video, the questions I saw here may not be the same questions that you see, when you go through the assignment yourself. But, all the objectives are the same. So I'm hoping that watching me do these here help you out in some way, when you're asked to do the assignment on your own. And thank you very much for watching.